Students, today we're going to investigate the Lewis Dots Lab that has a handout that you can find on Blackbaud. And in it, we're going to use a kit that involves beads and laminated cards. In doing that, we're going to represent the valence electrons found around atoms, both individually and in compounds. So this card has a nucleus in the middle, and then 4 boxes representing the orbitals of the second principal energy level, which would, or can fit in that principal energy level and would represent the valence electrons. So let's start. They ask us in the lab report to start by representing individual neutral atoms. It's going to be very helpful to have a periodic table so that you can refer to the atomic number. Remember, if an atom is neutral, it has the same number of electrons as protons. So if I know, for instance, the first one listed is boron, and I can see on the periodic table that boron has 5 protons in it, then that means that I should have 5 electrons. So here's my card representing the atom, and I'm going to select, without reference to color right now, the color of these beads, I'm going to represent 5 electrons by placing the beads in the boxes around that central atom. And let me angle this camera so you can maybe see it a little better. Okay, so I've got in one of these boxes, I'm going to place a couple of electrons. I need 5 in total. And I'm going to try to reflect some knowledge of the order in which orbitals are filled. So the 2s sublevel would have 2 dots, or 2 beads in this case, and 1 in each of the other boxes, representing 1 electron in one of the 2p orbitals, 1 electron in another 2p orbital, and 1 electron in the third 2p orbital. Okay, so then I'd snap a photo of this card, which represents neutral boron. The next element has, let's see, if I go from left to right, I'm seeing strontium. So now strontium on the periodic table, this is one of the bigger elements, or bigger atoms. It's got 38 protons in it, which means I'd have in total 38 electrons, which is like a lot. But all I need to show is 2 valence electrons. So I'm simply going to take away 3 of the beads from the previous card, and you can arrange them however you want. I'm not really worried about exactly how they're arranged, but I've got 2 valence electrons. Snap a photo, and that represents neutral strontium. The other 2 elements listed in individual neutral atoms, we have germanium, and then we have xenon at the end. So let's find those elements. Germanium is in column 14, right below carbon. So that means it has 4 valence electrons. And I might space them out like this. Again, I'm not particularly concerned with how they're arranged. I just want to see 4 beads around. That's the nucleus representing valence electrons. So 1, 2, 3, 4, snap a picture, and you would have germanium's representation. And then the last one, xenon. Okay, xenon is way, way, way over here on the right side of the periodic table. It's in the noble gas column. That's the column if you exclude helium, which is kind of a rare exception with only 2 valence electrons. All the rest of them, neon on down, have 8 valence electrons. So now we've got to add more beads until we get all 4 of these orbitals filled up. I've got now 1, 2, 3, 4, 5, 6, 7, 8 dots representing the 8 valence electrons in neutral xenon. Then they go on to ask you about representing monatomic ions, or single atom ions. Magnesium ion. Let's start by representing neutral magnesium. So I'm going to remove these beads. Let's find magnesium on the periodic table. It's over here in column 2. Column 2, those elements have 2 valence electrons. Okay, so I'm going to start by putting a couple of beads on this card. That would represent neutral magnesium. Now, what's the charge of magnesium ion? Magnesium ion, along with all the other elements in column 2 that form ions, would take a +2 charge. If you have a positive charge, that means you've lost electrons. If you have a positive charge, you've lost electrons. And if the magnitude of the charge is 2+, then you've lost 2 electrons. Aha, an empty card. Snap a picture. That's magnesium ion. Next one. I've got potassium ion. Okay. Potassium on the periodic table is in column 1. So let's start with neutral potassium, 1 valence electron. And the charge on potassium ion, along with all of the elements in column 1 when they form charged ions, would take a +1 charge. So again, we're going to lose electrons. We're going to lose 1 electron because the magnitude of the charge is 1. Well, I've got 1 valence electron here. Take it off, snap a picture. It's an empty card. That's potassium ions, what it looks like in terms of valence electrons. Notice there's a pattern here, right? An empty card means it's ready to bond. Now, the other 2 ions, oxygen and bromine, those are going to go the other way. So let's start by identifying oxygen's position on the periodic table. Column 16, that's the column that would have 6 valence electrons when neutral. So I'm going to start by placing 6 beads on the card. Okay, that's neutral oxygen. I'm sorry, I need 6. One more. Okay, that's neutral oxygen. Okay, neutral oxygen has 6 beads. Oxygen ion, along with all the other elements in column 16 when they form ions, will take a 2- charge. The negative charge means you've added electrons. And if the magnitude is 2, then you've added 2 extra electrons. So I'm going to place 2 more beads on this card, filling it up. So I have 8 valence electrons, and I'm going to snap a picture. The O2- ion looks like this. Next one, bromine. Neutral bromine is in column 17. Okay, so neutral bromine would have 7 valence electrons. Bromine ion will take a -1 charge along with all the other halogen elements. The elements in column 17 take a -1 charge. So that means add 1 more electron. And when I do that, I get the same picture as I had with oxygen ion, a filled up card. Take a picture, and that represents bromine ion. There's a reason to this and a pattern for this. Okay. Now we're going to go on to the compounds. They're asking us to consider combining lithium ion and fluorine ion or fluoride ion. So now I'm going to take out another card, and I'll start with neutral fluorine and neutral lithium. Okay, neutral fluorine, neutral lithium. Fluorine, same column as bromine was. So column 17, 7 valence electrons, as pictured here. When it forms an ion, it gets 1 more. Okay, so a filled up card for the fluorine ion. Lithium, way over here in column 1, if it's neutral, will have 1 dot in it. So this one's going to represent lithium. This card represents fluorine. When it forms an ion, like all elements in column 1, takes a +1 charge. So that's actually the removal of 1 electron. And so what we're going to do is, if you have an empty card and a full card, I'm just going to overlay the 2 of these right on top of each other, showing the formation of lithium ion and fluorine ion together to make an ionic compound, lithium fluoride. Snap a picture of that. Okay. Next, we've got beryllium oxide. students, you're going to start to see a pattern here. Oxygen in column 16 would have, let's distribute these a little bit. Oxygen in column 16 has 6 valence electrons when neutral. When it forms oxygen ion, like we've done before, you gain 2 electrons. So now it's a completely filled card with all of the spots filled up, 8 valence electrons. When it pairs with beryllium, okay, now let's consider neutral beryllium, column 2, Be is its symbol. It has 2 valence electrons initially. When it forms an ion, it takes a 2+ charge. So those 2 electrons that it originally had go away. We now have beryllium ion and oxygen ion, or oxide ion. And to form the compound, simply overlay the 2 cards, and you've got a compound, beryllium oxide. Hey, that looks exactly like the previous compound, lithium fluoride. Well, there's a reason for that. There's a pattern that we're forming here. Okay, so snap a picture. You've got beryllium oxide. BeO is its formula. Next, we've got cesium and sulfide. Okay. One of the challenges is simply finding these elements on the periodic table. Sulfur is in column 16, right below oxygen. Cesium's pretty far down low in column 1. CS is its symbol. Okay, so if it's neutral, the cesium would have just 1 valence electron on it, and sulfide would have 6 valence electrons. So if you count them up, this is my neutral sulfur, this is my neutral cesium, and then I'm going to think about, how can I fill up the sulfide ion so that it has a complete valence shell, and make sure that cesium has an empty valence shell so that it would be attracted to it and bond? Well, I'm going to take another card out, because in this case, it requires 2 cesium ions to bond with 1 sulfur. Now watch this. The lone electron lone valence electron on one of the cesiums jumps onto sulfur in this position, and the other one jumps onto cesium in this position. And look, we have now a compound of cesium sulfide that consists of 2 cesium atoms and 1 sulfur atom. So CS2S is the formula for cesium sulfide. Let's try another one like this. Calcium bromide. So now we're going to consider calcium. Let's get rid of this. On the periodic table, calcium is in column 2. So it takes 2 valence electrons. That's my neutral calcium. And then they say bromide. Okay, bromine, we know where that is. Column 17, the halogens. I'm going to put 7 valence electrons around the nucleus in these. So here's a neutral bromine. And guess what? I'm going to need another bromine atom in order to make this compound, because I need a position for the two beads on calcium. There's only 1 spot for it to go in the first bromine atom. I'm going to need a whole other bromine atom with its own 7 valence electrons when neutral in order to get a position for it. So I'm just arranging my beads. Now I have 7 in this card. That represents neutral bromine. 7 in this card representing neutral bromine. 2 on this card representing neutral calcium. Okay, so now let's consider what happens. Calcium forms a 2+ ion, meaning it gives up 2 electrons. And each of the 2 bromines would form a 1- ion, meaning that they each gained an electron. And if I can represent this with the cards, I'd overlay the cards in such a way that I've got 2 completely filled valence shells for the bromine and an empty valence shell for calcium. It doesn't have to be the central atom with the beads. It could be the central atom without the beads. That's what we see here. So snap a picture, and we've got calcium bromide. The last challenge in this lab is to consider covalent compounds. So now they invite us to consider the fluorine molecule as the first one. So I'm way down at the bottom of the handout. Fluorine molecule is one of the diatomics. It's F2. And so I'm going to start with 2 neutral fluorine atoms. So 2 cards with 7 beads each. And then I'm going to try to think about how do these 2 atoms bond in such a way that they both attain access to 8 valence electrons. Well, students, by sliding the card one under the other, we can see that there are 2 shared electrons. These electrons in the middle are shared between those 2 atoms, giving us an F2 molecule with each fluorine atom having access to 8 valence electrons, which is following what they call the octet rule, meaning it's happy. Okay, so that's the F2 or fluorine molecule. Snap a picture of that one. They next invite us to overlap these selenium dichloride. Okay, selenium dichloride. I'm going to start with chlorine. And since the prefix di in the name indicates 2 of them, I'm going to put 2 chlorines together, each of which would have 7 valence electrons. So here's my 2 chlorine atoms. Each have 7 valence electrons. Selenium, now this is an interesting one. Se is right under sulfur. It's in column 16. So I'm going to pull another card out, and I'm going to place 6 beads around it, because elements in column 16 have 6 valence electrons. Okay, so I'll try to think about this. How does this atom, which would be the central atom, connect to these 2 atoms, which will be the satellite atoms? First, I'm going to position the central atom in the middle, and then I'm going to think about how can we share electrons in such a way that every atom in the compound has access to 8 valence electrons. Well, what if I rotate this one by 1 position? I think I'm going to slide this bead over. Now, if the central selenium bonds with this satellite chlorine, you can overlap the card. Aha! We've got access to 8 electrons for one of the chlorines. And then let's slide this one over, indicate the sharing of another valence electron. And now this chlorine has access to 8 electrons, along with the central selenium atom. Aha! Here we've got a compound where there's plenty of valence electrons. Each one has access to a full 8. Snap a photo, that's selenium dichloride. The next one they ask us to make is carbon tetrahydride. Ooh, CH4. We're going to need some more cards here because if you have CH4, that means there's 5 atoms altogether. One of them is going to have 4 dots on it, or 4 valence electrons. I think I'll distribute these thus. So here's my carbon with 4 dots. And then I should have 4 hydrogen atoms, each with 1 dot. Each with 1 dot. And I've got to figure out, okay, how are we going to combine these in such a way that carbon will have access to 8 electrons? And interestingly, hydrogen only needs access to 2 electrons in order to be a stable part of a stable compound. So I'm going to put the carbon in the middle, since that's going to be our central atom. And then I'm going to arrange 4 hydrogens around it. And I'm going to think about how do we share these so that carbon will have access to all of the valence electrons it needs. Well, here's one bond. So a carbon sharing an electron with a hydrogen. Here's another bond. Again, a carbon sharing an electron with a hydrogen. Here's a third bond, carbon sharing electrons with a hydrogen. And here's a fourth bond, carbon sharing an electron with a hydrogen. So if each bond consists of the sharing of one electron, then the central carbon has access to all 8 valence electrons it needs. And each of the 4 satellite hydrogens has access to the 2 electrons that it needs in order to be happy. So snap a photo. This is carbon tetrahydride. The last compound in this lab is a real challenge. It's going to involve 2 cards. Let me pull away most of this stuff here. So here are 2 cards. And in the lab handout, they tell you exactly how they should be overlaid, because we're going to represent a double bond here, which is an unusual, fairly unusual arrangement. Okay, so we're going to overlap the cards thus. And this compound is sulfur monoxide. So now sulfur and oxygen both have 6 valence electrons. They're elements in column 16. So if they each have 6, we have to bond them in such a way upon overlapping these. Start with them not quite as overlapped. They each need to bond in such a way that they have access to 8 electrons in the compound. So if this is sulfur and this one's oxygen, if we share an electron between the 2 of them in this box and share another electron between the 2 of them in this box and form a double bond, then they're really sharing, not just a pair of electrons, but two pairs of electrons, while retaining, each atom retains their own couple of pairs of electrons. Those are called lone pairs, and there are 2 bonding pairs as well. So this is representing a double bond. It's sulfur monoxide. Snap a photo, and then you can upload that to the report. And we'll have our Lewis dots structure made. Thank you for your good work on this lab.